In this video, we're going to look at a problem that was assigned for homework, and it is a simply supported beam. I've sort of written over it here, but you can see the simple support there, simple support there. Notice the size change, so we'll have to deal with that. Notice the distributed loading. There are lots of things that we could calculate from this beam. If we wanted to, we could calculate the deflection in the middle of this beam by placing a dummy load there and dealing with that. But that's not what we're interested in this problem. What I want to do is calculate the slope at this end of this beam, and this would be important because a ball bearing might go there, and ball bearings do not want shafts coming into them to have significant slope, so we have to keep that slope under control. In order to use Castigliano to calculate a slope, we have to have a moment at the location. Well, we don't have a moment at the location where we want to calculate the slope, so we're going to place a dummy moment at this left-hand end, at the spot where I'd like to calculate the slope. Eventually we'll set that dummy moment value equal to 0, but we place it there. I'm going to call it Q. Some of the details of the problem are given, but you've seen that in the problem statement. The first thing I need to do in the problem is place any dummy loads that are necessary. Then the next thing that I need to do is do any statics that's necessary. In this problem, I'm going to be measuring X from the left. Anytime I make a cut on a section, I'll be looking left. And so I do need to do the statics on this left-hand simply support reaction, and it'll have a force. I don't need to do that for this right-hand support reaction. But what I'm going to do is I'm going to sum moments about the right-hand side. When I sum moments about the right-hand side, I'll have a term from Q. I'll have a term from F, and I'll have a term from the distributed load. When I finally do all that properly, and you can check this, I get that my reaction at this left-hand side is 900 minus Q over 16, and I'll leave that for you to do more completely yourself. Now we're ready to start with Castigliano, and so I'm only going to be paying attention to bending, but I've got to write bending equations in 3 different locations. Region 1, no load and a small size. Region 2, load is given and a larger diameter. Region 3, again, no load and a small size. I'm going to write my moment in each region, and I'm going to take the partial of my moment with respect to the dummy load Q. So in the region between, as X goes from 0 to 3, my moment equation will have a term Q. It'll have a term from this force F times a moment arm of X. So it's going to be Q plus F, which is 900 minus Q over 16. That's the moment arm. That's the force times the moment arm X. Okay. Notice I've already set these Q's equal to 0. In fact, I haven't done that yet. Before I set the Q's equal to 0, I take my partials with respect, partial of this moment with respect to Q. I get a 1 term out of here, and I get a minus X over 16 term out of here. And so that's my partial of moment number 1 with respect to Q. Now I can set those Q's equal to 0. Notice I said here, set the Q's equal to 0 after the partials are taken. The next step then is to write moment in region number 2. It includes everything in region number 1, and before you saw me write M1 of X right here, which would be perfectly fine. These 2 terms come from the moment number 1 term. But in region number 2, we also have a term that involves this distributed load. And that distributed load term, I will leave it to you to show that it is the load W to the left of where I'll be making my cut, which would be W times X minus 3. And then the centroid of that load W would be an X minus 3 over 2, so we get a WX minus 3 squared over 2 with a minus sign on it. Okay, you might want to pause and just do that one for yourself and double check it. Make sure that you can do that. Turns out there's nothing involving Q in this term, so my partial of M2 with respect to Q is the same as the partial of M1 with respect to Q. The final step then is to find the bending moment in this region. It's going to involve everything that was in region 1, but in this region my load is stopped, and so I have to write a different description of this distributed load. And scrolling away, it's going to be everything that was in the first region, and then My entire distributed load is W times 10. My moment arm for that distributed load from my current value of x is x minus 8. Again, do that one for yourself. Just make sure that you can write out equations like that. And my partial of that moment with respect to Q is the same as all the others have been, because there is no Q in this region. Now finally I get to the Castigliano piece, and that says that if I want to find a slope, I'll be taking a partial with respect to a moment. So I have a moment Q. I've taken my partials with respect to the moment. So the slope at the location of my moment Q is 1 over EI, M1 partial of M1 with respect to Q, M2 then the partial, M3 and the partial. Notice in my first region, where that goes from 0 to 3, I'm using I1. In my second region, from 3 to 13, I'm using a bigger I. We'll call that I2. And in my final region, this is a little messy, from 13 to 16, I'm back to the smaller value of I. Plugging in my equation for the moment in the region 1 after Q was set to 0. And we can see that in this piece, although this is M3. This is still the region 1 piece. Q goes to 0 here, Q goes to 0 here. I'm left with 900 times x. So in region 1, 900 times x times my partial. In region 2, 900x minus my distributed term times the partial. In region 3, 900x minus the distributed term times the partial. What this will give me is powers of x when I multiply everything out, and so this will be polynomials in terms of x. Those will integrate very easily. I plug in my limits of integration very carefully, and I then have calculated the slope at the end of the beam.